Hey everyone, we're going to continue our discussion with the Fermi gases and the Bose gases by coming up with a little bit more equations dealing with them. Last time when we talked about it, we basically only really came up with the average occupancy equation, but we didn't really do anything extra with it. Now, if you recalled before, the difference between a Fermi gas and a Bose gas is their ability to cohabitate within the same levels. So, for example, this picture really does kind of perfectly describe the difference between a Bose gas and a Fermi gas. With the Bose gas, if you remember, they're the ones that were allowed to have any number of particles at any level. So when you get to a low energy Bose gas, it's possible that you can have all your particles in the lowest level, in that bottom ground state energy level. Unlike with the Fermi gas, where you're excluded by the Pauli exclusion principle to only having 0 or 1 particles of the same type. So, for example, here, if you stack them all up, one particle going to each level, there is a maximum level that it will reach, and this is actually what we call the Fermi energy, or the Fermi temperature sometimes. That highest energy level, if you stack everything neatly in its least likely state, I guess you could say. Now, as we said before, fermions and bosons act exactly the same way when we're in the classical regime, where the concentration is much lower than that quantum concentration. And we only really get the distinct differences once we enter into the quantum regime. Now, uh, um, some characteristics of Fermi gases and Bose gases are on here. Like, for example, Fermi gases have very high kinetic energy and very low heat capacity, low magnetic susceptibility, low interparticle collision rates, and high pressure on the container. While boson gases have high concentration in ground orbital and will end up acting as a superfluid. This is something with zero viscosity. So if you haven't done so already, there's a senior lab course in physics where one of the things that you will do is work with a superfluid helium type state, and that's pretty much this boson gas. I remember when I was doing the college, the senior lab course, I had to do a. I'm trying to think of the exact name for it. It was called the Lab of Second Sound, and basically we had to measure. I believe it was um, heat rate or heat flow through a superfluid helium material. Um, so yeah, you'll get to play around with this later on. It is pretty interesting to see the difference between a fluid and a superfluid. All right. Now, one thing that I want to mention is typically we use concentration as a way of defining whether something's in the quantum realm or not. But concentration is really hard for us to actually identify and really measure properly. So a lot of times what we do is we instead rewrite that our definition for the quantum regime from being a dependent on concentration to being more temperature based, a temperature definition. As we know, when you decrease the temperature, you do decrease the volume, and it will end up decreasing the overall concentration as well. So what we do is we just take the our definition for the quantum concentration and rewrite it in terms of temperature, like this. So this is what we end up having. So now what we can say is that if our temperature, that this is our, if you can think about it, the quantum temperature, if the temperature of our gas or our material is lower than this, then it will be in the quantum regime, sometimes also called a degenerate gas. Pretty much the same thing as this definition, but now as a more related to temperature. And this is definitely a lot more useful. In fact, I believe for superfluid helium, it doesn't reach that superfluid state until it gets to around like 2 degrees Kelvin. It becomes a lot easier for us to identify whether a gas is in the quantum realm based off of temperature, because that's something that we can easily measure rather than concentration, which definitely is a lot harder because how do you know how many moles or particles you have within the container? And while finding the volume is easy, you never really know how much of the volume is um, taking up. All right, so if you recall, we had this equation for the average number of particles within some energy orbital. It was based off of this. This lambda, of course, can be replaced with a n over nq. Um, and as you know, I said this before that with fermions, um, they're limited by the Pauli exclusion principle, so occupancies can only be either 0 or 1. Um, and then at lower temperatures, the all those energy low orbitals will only have one fermion each. Like I said, it'll pretty much stack nicely. All right, so when you end up reaching absolute zero, so this is usually what I'm referring to when I say low temperature states or low energy states scenarios. What we end up getting is that every orbital that is below this Fermi energy is going to be occupied with by exactly one particle, and that all the orbitals that are above this Fermi energy level will end up having no occupancy. Yeah, so this is another way of saying it. I know I did go over this in the previous video, but I don't think I really explained it perfectly, or at least I didn't really go into as much detail. So this is another way of kind of explaining it, is that it's the lowest energy, such that there are just enough orbitals to hold all the particles in place. So again, if you kind of organize it so that you have just as much particles as you can in every single orbital level, based off of the Pauli exclusion principle, the Fermi energy is that highest energy level. And then this is just restating what I said before about how bosons, due to their integer spins, are not limited by this Pauli exclusion principle. So they don't have this limit on how many particles can go to each energy level. For something at the absolute zero, they have all their particles at the ground level. So that's the main difference between the boson gases and the Fermi gases. Um, yeah, so again, this is just restating it that this really only occurs while it says that while we said that at absolute zero, all the energy levels below that Fermi energy are occupied, while all of it above are unoccupied. What this basically says is that if we are talking about a quantum gas or a degenerate gas, one where the temperature is less than the Fermi temperature or the quantum temperature, then what we end up having is we have something similar where uh, we still have most of our particles occupied within that below the Fermi energy, but not all of them are occupied. And we do still have mainly all our particles above the Fermi energy unoccupied, but not all of them are unoccupied. So it's just basically saying that we're in the process of getting all the particles to fall below the Fermi energy level and start to occupy those lower orbitals. So here it says, here's an example. If we have a system that has 8 electrons, the ground state would have the electrons occupying the orbitals with 1, 2, 3, and 4, and then each of them are plus or minus one half. So there's a plus minus one half spin in n1, in n2 there's a plus and minus one half spin. So remember, we're saying that particles can only be occupied by 0, 1 of the same type. By same type, we're talking mainly about that spin. Uh, Particles can come in as spin up or spin down. So you can have one example of a spin up and one of a spin down in this level one state, and that would count as not violating the Pauli exclusion principle because you're only having one spin up and one spin down. This is also why I think in the previous definition of the Fermi energy level, I had mentioned that it was half occupied. That was because of the whole one. There was one spin up, but there was no spin down. So that's a possible setup. Here, so if we rewrite the equation that we have for what the Fermi energy is, we had this equation. Now, I'm briefly going to explain this, but not really to go into too much detail. So n here is going to be used as a definition or as representing the radius of a sphere that separates the filled and empty orbital. So like if you take that, because remember we're talking about like a three-dimensional particle and all like the electrons around the particle. If we are looking at like a sphere that is going around that atom, NF is that the radius that's separating the lower orbitals with the higher orbitals. And we could find the number of particles by pretty much doing what we did the last time. If you remember, I had said before that we're going to do something where we, take two and then we times by 1/8 of a sphere in order to find the density. Yeah, we're doing pretty much the same thing here. Two because of the whole spin up, spin down, 1/8 of the sphere, yada yada yada. But what ends up really being more important is just this definition that the Fermi radius is represented by this equation. So if we take our Fermi energy equation, we can rewrite it so it looks more like this. So now it's written in a little bit more terms of things that we might actually know. Like we would most likely know the number of particles, or more so than this. Of course, we can combine the n and the L cubed because L cubed is just a volume. So we can combine them together to just be defined as the concentration. And as we said before, this is being defined as the Fermi temperature. All right. So like we said before, the Fermi temperature and the Fermi energy are the same thing, just slight terminology difference. All right. So we can end up finding the total energy, as we always do, by just adding the energy from the ground state all the way up to whatever that highest energy state is. So in order to do this, we want to turn that into an integral. Our equation will look something like this. Then what we want to do is try to get all the n terms together. It ends up boiling down to being an integral of n to the fourth, which is a fairly easy one to integrate. We end up getting this. So what we can do from here is replace some of the n terms, because what we're going to want to actually do is we don't want to replace all of these nf terms because we kind of want to go back to the using the Fermi energy. So we only do some of them. In fact, NF to the third, we basically replace with this. And then we're left with this term, which can now all be combined together so that we can replace it with the Fermi energy. So this is just taking that energy level and replacing it with this. Now, note this does kind of actually look very similar to the equation we had for the internal energy for a classical ideal gas. Because remember, the Fermi energy can also be defined as the Fermi temperature. And the equation that we had for the internal energy was 3 halves n tau. So here, the total energy for this degenerate gas, this quantum gas, is 3/5 n tau f. So pretty interesting to note the relationship. Um, so here, this is kind of mentioning that as if we look at this equation, I guess this one, concentration one, as we know, as we can see, as the volume is decreasing, this energy ends up increasing, and this ends up resulting in a repulsive nature within the materials. And this is what's basically balancing out the gravitational force within stars like white dwarfs and neutron stars. So basically, as you know, like with those, it's a very dense thing. The gravity is pulling it in really hard. So something has to be kind of counterbalancing the gravitational attraction of all the particles. And that's pretty much this. All right. So pause the video. Oh, here's a practice question. Work on this self. Pause the video, and we'll go over it in a second. All right. So here we have a white dwarf star. They give us a They tell us that it has a mass and radius, and they tell us that the electrons are degenerate, the protons are non-degenerate, and they want us to show that the gravitational self-energy is essentially this. So we had done this before. There was I can't remember the exact video we did this in. It was either the previous lecture video or the one before that. Um, but basically, we take the equation for the gravitational potential energy, where the two m's are the mass of the shell and the mass of the interior. The mass of the shell being like the very outer edge that we're kind of removing, and we replace them with the partial derivative, I guess, of the shell, and then the actual mass of the inside based off of the density. Then from here we plug in some numbers. We rewrite everything in terms of r, integrate it, and we end up getting something that looks like this. Clean it all up. You know, r to the fifth crosses out with 5 of these r's. The 16 crosses out with the 16, though that doesn't really matter. All that really matters is that we have a g, an m squared, and an r in the denominator. So yeah, here's the next question. Pause the video, work on the self, and we'll go over in a second. All right, so what they want us to do is show the kinetic energy of the electrons in the ground state is given by this equation here. So what we're going to do is we're going to take the energy that we have and use this form of the equation because we don't really want to keep it in terms of this Fermi energy. It's not something that we have up here. So instead, we kind of replace all of the replace that EF with the other definition that we had or that we're able to substitute in for. Now, the number of electrons and the number of protons are going to be equal, and it's found by taking the mass and divide it by mH. This is the total mass of the sun divided by the mass of the hydrogen atoms inside of it, and that's going to give us the total number of particles that we can plug into here. And then we also know that the volume, because it's a sphere, is given by 4/3 pi r cubed. So plugging these two definitions in for both n and v, we end up getting this, which when we clean it up and move things around, ends up being this. All right, so exactly what they wanted up here. M, MH, R, M. There you go. All right, here's the next part. Pause the video, work on itself. We'll go over it in a second. Um, yeah, so they want us to show that if these two energies are of similar order of magnitudes, then this is going to be true. So what we're going to end up doing is basically setting these two equations equal to each other, or at least that's how we're going to start off. Remember, all these questions build from the previous part. So if you're doing something in part A, that's going to be most likely used later on in either part B, part C, or so on. So always kind of keep that in mind. So when we set these two equal to each other, again, we move things around. They want us to have this. So we're going to just keep all the, bring all the masses and all the radius terms to one side. And we do end up getting m to the 1/3 times r. And then we have all these terms, which are all constant terms, it turns out. So now what we can do is plug in the numbers that we actually have for all these terms. Like mH, as we know, is the mass of hydrogen. This is a given constant. This is the mass of an electron. And we end up getting this. So we do end up getting exactly what they wanted. All right, here's the next part. Pause the video, work on the stuff, and we'll go over in a second. All right. So they want us to figure out the dwarf of a white dwarf. Sorry, the density of a white dwarf. And they're giving us and saying that we're going to assume that this white dwarf has the same mass of as our sun. Um, so yeah, we just kind of use the equation that relates density to mass and volume. So we now have a definition for the mass. To figure out the radius, we can actually use what we just found in part C. Now, what I did here was I took the equation that we had and I just rewrote it so that it was that it solved for r essentially. Uh, but you don't have to do that. If you wanted to, what you could have done is just taken the equation that you got from part C, plugged in the mass term in for m, solved for r, and then plug that into here. It doesn't matter. Either way, ends up working out the same. When you plug the numbers in, you should end up getting that the density is about 3.27 times 10 to the fifth. Note that how drastically higher that is to our sun's density. Our sun has a density that is basically a little bit higher than 1. So white dwarfs do have a fairly high density. It's one of the main reasons. Well, didn't really want to get into that, but that's more astronomy stuff. But yeah, they are extremely small, lots of mass in one little area. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so they want us to basically show two things. So we're coming out first. We're gonna slightly change what we're working with to be more of a neutron star. But they want us to show us first that this relationship is going to be true for the neutron star. And then they want us to show or figure out what radius the neutron star would have to be so that it has a mass equal to the sun. Um, so we kind of do the same thing that we did last time, except here, the little m that we had here, the one that was for the electron, now becomes of a neutron. Um, what we can actually do is just say that it's the same as hydrogen atom, because as you know, hydrogen atoms are proton is a single proton and a single electron, which just so happens to be the exact mass of a neutron. So we can actually just replace the mass of a neutron with the mass of hydrogen so that we can actually combine it in with this term. We do the same thing where we just bring the mass and radius to this side, and we leave all the constant terms here. When we plug the numbers in, we end up getting that it's equal to 7.8 times 10 to the 16th. So again, very close to what I have up here. Then solving for the radius, we end up getting that the radius should end up being 6.2 times 10 to the fifth centimeters. So fairly small. Now, they didn't ask for this, but just to show the comparison between the neutron star, the sun, and the white dwarf, the density for this would end up being 2 times 10 to the 15th. So again, extremely dense. Neutron stars are essentially uh, I should say, one step away from being black holes. If you don't know, when a large, massive star goes to that ending state, if it doesn't have enough mass to become a black hole, it becomes a neutron star. So it does kind of make sense that this is even more dense than the white dwarf, which is what happens at the end of a low, small mass star um, near its death. I'll mention a few more things with the Fermi gas before I end the video. So we can find an equation for the pressure of a Fermi gas as we reach this absolute zero temperature. So as we know, this is the energy that we have at the low level. Then what we can do is actually replace, so we have this term of N and V. Now, as you know, pressure is this equation, the partial derivative of the energy, the internal energy with respect to the volume. So now that we have this in terms of volume, we can just take the partial derivative of this, and we end up getting, uh, when it's cleaned up, we end up getting this. So again, something very similar to what we normally get with the ideal gas law, except instead of PV equals N tau, it's now PV equals 2/5 N tau F. Now, you should note a lot of the stuff that I did. Once again, most of the things that you do in this case comes from the fact of knowing what you want to try to get. So the fact that most of the stuff in this equation is unchanged with only really the the additional 2/3 and the I guess the change in this exponent, not much has changed from having EF in this term or TF, doesn't matter. So what you would want to do is try to actually get that back. Now, the way we would do this is by trying to rewrite this into the similar terms that would give us the Fermi energy. So that's what they did here when they combined this n over v to the 5/3. They basically split it up into a 2/3 and a 3/3, I guess, if you want. So now that we can replace this with EF and then rewrite everything so that it kind of looks very similar to our ideal gas law. Yeah. Um, so once again, we could do this whole thing with the average values. Remember, every time when we want to do average of anything, it's always in weighted sum. In here, though, the weight comes from this occupancy term. We can end up replacing this with a integration. Again, I'm not going to go into too much detail with this. This is what we did, the density of states that we did before, yada, yada, yada. So, and when we take that energy, we can rewrite. So this is the number of particles based off of their energy levels. Again, something that we've done before. We could take the ln term of this, take the partial, and this is actually defined as the density of state. So combining it all together, it looks something like this. So this is what we define as the density of the orbital states. From here, so we can use this to figure out the number of electrons and the total energy by taking the integral. And then from here, so if we're looking at the ground state scenarios, because of the fact that all the orbitals are filled up under this energy, this Fermi energy, we can actually change our integral from being 0 to infinity to 0 to the Fermi energy, because that's going to be the highest level. Let me pause the video. We'll stop the video here. Actually, you know what? Let's continue. We'll continue with this because I think this is the last thing for this. So pause the video, work on this up, and we'll go over it in a second. All right. So what we want to do is take this density and show that for a one-dimensional free electron, it will look something like this, and then for two dimensionals, it will look something like this. All right. So when you have a one-dimensional orbital, the number of electrons is going to be 2n. So when we take our equation that we have, it'll end up being rewritten like this, which for the number of electrons can be replaced with this equation. And again, we kind of just go through the same terms that we did before, take the ln of it. Of course, we only really care about this energy term. Everything else is just going to be a constant. Take the derivative with respect to n and e. This ends up being equal to this density term. So solving this, essentially, we end up getting exactly what they wanted up here. That's pretty much it. And then for the second two dimensions, we're gonna pretty much do the same thing. Here, the number of electrons will end up being equal to this. Again, coming very similar to what we had before. And we go through the same process, take the ln of both sides, only care about the the n and the e terms, so move everything to one side but the dn, set it equal to this, and then just solve and simplify, and we end up getting exactly what they wanted up here. And that's pretty much it. Alright, we'll stop the video here now. If you have any questions, please let me know. Otherwise, I'll see you later.